When you talk to the most forward-thinking engineers in responsible AI, they all seem to land on this one core belief, and our sources put it perfectly,
What's that?
that a model can be fast, fair, and beautifully explainable, but if it isn't private, it won't be trusted.
Ah, yes,
Think
absolutely.
about that. Privacy isn't, a checklist item anymore. It's not a luxury. It is the absolute foundation for any trustworthy AI system we build today.
Precisely. Without that foundation, you just lose everything. You lose customer interaction, you lose the model's utility, and at the end of the day, you lose the business case for it. We're really way beyond just talking about privacy in theory now.
Right.
The conversation today is all about the practical architectural solutions.
And that's exactly our mission for this deep dive. We are moving past the why and we're getting deep into the how. We're going to unpack the three-layer architecture that organizations handling the most sensitive data, your banks, your hospitals use to actually engineer privacy into their systems.
And the pressure to do this is just immense. It's really coming from two directions. First, you've got the strict global regulations.
Like GDPR.
Exactly. GDPR in Europe, the CCPA in California, Singapore's PDPA. And failure to comply comes with these massive, massive penalties.
And the second force has to be the customer.
Absolutely. Customer trust is so fragile.
Mm.
If your users think your AI is leaky, or even if they just feel a little exposed, they will stop using your app.
Mhm.
And that damage can be, irreversible.
Now, when we talk about data exposure, we have to talk about the specific threat this kind of engineering is designed to fight. It's
Okay.
much more clever than just a simple data breach.
It is. The threat is called model inversion. Imagine a really clever hacker. They don't even need to steal the training data directly.
Okay.
They just interact with an unprotected model over and over again. And based on how it responds, they can actually reverse engineer personal identities, names, addresses, health conditions, just from those interactions.
Wow, so they could literally reconstruct the data that was used to train the model.
Which is terrifying. I mean, think about the potential for fraud or social spoofing.
So let's just clarify the goal here. What does private AI really mean in this kind of high-stakes world?
It means providing a mathematically verifiable guarantee. No one, absolutely no one, should be able to figure out personal details about an individual just by interacting with the model.
Even if they know almost everything else.
That's the key. Even if a bad actor knows the entire training data set except for one person, they should still not be able to identify or learn anything meaningful about that single individual.
That is a high bar.
Oh, yeah.
Okay, let's unpack this three-layer approach. I like to think of these as sort of three safety shields that stack up.
It's a great analogy. They really do cover the entire AI pipeline from the moment the data is collected to the moment a prediction is made.
So, shield number one, operational privacy. This one seems like the most straightforward.
It is the simplest to describe, yes, but maybe the hardest to maintain perfectly. Operational privacy is fundamentally about where the data lives. Instead of sending sensitive information across the internet, everything stays securely in-house, within the organization's own secure environment.
So you're talking about things like air-gapped systems, or at least secure on-premise servers. Basically, you reduce the attack surface because the data never even touches the outside world.
Exactly. For high-security places like defense contractors, yeah, it often means fully air-gapped, physically isolated networks. For a big bank, it means really tight access controls, or maybe using things like secure enclaves where the processing happens in a certified, isolated part of the chip. The point is, the data owner keeps total control.
Okay, so that secures the physical location. Now for Shield 2, model-level privacy. This is where we shift from physical security to math.
Right, to the mathematical guarantees. And this is where differential privacy, or DP, comes in. This is the core engine.
And this happens during training.
Yes, this layer injects privacy guarantees right into the training process itself. We use specialized libraries for this, like IBM's diffprivlib or Opacus, if you're using PyTorch. They handle all the complex math so engineers can focus on the configuration.
And finally, layer 3, federated privacy.
This is the layer for when you need global knowledge, but the data has to stay local. The data truly stays where it belongs, a local bank branch, a regional hospital, you name it.
So how does the learning happen?
The brilliance is that a central model only collects the learned weight updates from those local models. It never, ever sees the raw data itself.
Okay, that is a beautiful framework. Let's zoom in on that second layer, differential privacy, because this is where engineers really face that core mathematical trade-off.
It really is. DP gives us that quantitative guarantee we were talking about, and the core mechanism is actually pretty simple to understand.
Which is?
To mask the contribution of any single individual in the data, you add carefully calibrated noise to the model's parameters during training.
And we know that adding noise always comes at a cost, right? It's just unavoidable that it's going to degrade the model's performance, at least a little bit.
The entire field of DP engineering is about managing that very trade-off. And the key metric, the main turning knob we use, is called privacy loss, or epsilon.
Okay.
A small epsilon means you've added a lot of noise, so you get very strong privacy, but you might be crippling your accuracy.
And conversely, a large epsilon means less noise, better accuracy, but your privacy guarantee is much weaker.
So the goal is always to find that sweet spot, that exact configuration where the model is still highly useful, it's still making the bank money or helping a patient while offering a robust, meaningful privacy guarantee.
Let's make this real. The source material had this great loan approval scenario. A bank is trying to predict loan approvals based on income, credit history, that sort of thing.
Right.
And the baseline, the standard non-private model, had an accuracy of 0.608. That's our starting point.
Okay. Now, what happens if we go to the absolute extreme for privacy? Let's just slam the dial all the way up and test an epsilon of 0.1. Super, super strong privacy.
I'm guessing the model is basically flying blind at that point.
It is. The accuracy just plummets, all the way down to 0.524. But look at the F1 score. That's what takes the biggest hit.
And for a bank, the F1 score is critical, isn't it?
It's everything because it balances precision and recall. Low precision means you're approving risky loans and losing money. Low recall means you're missing out on good customers and losing money. It's a balancing act.
So at epsilon 0.1, the noise just completely overwhelms the signal from the data. The model is unstable, unusable.
Totally. It becomes too cautious, maybe too erratic. You can't trust it. So the engineers have to ease up. They have to gradually increase epsilon.
And when did they start to see the model hearing the data again? What was the breakthrough finding?
The sweet spot, that critical balance landed right around an epsilon of 2.0.
And what did the performance look like there?
At epsilon 2.0, the model was still incredibly useful. The accuracy was 0.594, which is a tiny, negligible difference from the non-private baseline of 0.608.
Wow.
And crucially, the F1 score was virtually identical to the original non-private version. This is the holy grail of DP engineering. High utility, strong privacy.
And if they went past that, say to an epsilon of 5.0 or 10.0?
The trade-off curve just flattens out. At those higher epsilons, yeah, the accuracy is nearly identical to the baseline, but your privacy protection becomes what you might call privacy light. It's almost symbolic.
So you get diminishing returns.
Exactly. You sacrifice most of your meaningful privacy guarantee for almost no measurable gain in accuracy.
So we've established epsilon is the master knob. But here's the complexity, and this is what happens in the real world. Privacy isn't just about epsilon alone. It's a multidimensional problem, a whole configuration space.
That is the engineer's daily reality. You can't just set epsilon and walk away. You have to perform a parameter sweep, running the model dozens, maybe even 60 times, like they did in the source, changing multiple key settings at once to find the optimal combination.
Okay, so let's meet the other two knobs they were turning, date norm and C. Let's start with date norm. What is that actually doing?
Date norm is all about controlling individual influence through a process called clipping. Remember, for DP to work, no single data point can have a disproportionate effect on the model.
Right.
So if one person has an extraordinarily high income, their data point could, potentially break the privacy guarantee for everyone else.
So clipping just puts a cap on it. It says, we'll only count your income up to this maximum threshold, no matter how high it actually is.
Exactly right. Each data point is clipped to a maximum size defined by date norm. If you set it too low, you're clipping too aggressively, and the model loses important information. Set it too high, and the privacy guarantee gets weaker.
Then what did the experiments find was the sweet spot for that parameter?
The sweet spot was consistently in a moderate range, between 3 and 5. That gave enough signal for the model to learn properly without violating those privacy bounds.
Okay, now for the second parameter, C. This is the inverse of regularization strength. How does a standard machine learning setting like this interact with all this privacy noise?
It's all about stability. When you add DP noise, you are fundamentally making the learning process unstable. So your best defense is a stable, robust model to begin with.
And regularization forces the model to be simpler, less prone to overfitting.
Which is critical because a simpler model resists the noise better. So a lower C value like zero point 0.1 or 1.0 means stronger regularization, and that makes the model more robust against the DP noise.
So if you use a high C, say 10.0, the model gets more complex and it just amplifies the instability from the noise.
You got it. The practical tip is usually to start with C equals 1.0. It's a really good balance.
So the big insight from all those 60 experiments was that DP is never just one setting. It's an entire ecosystem of variables you have to tune together.
Absolutely. The best trade-off consistently came from tuning all three at once. A moderate epsilon, a moderate data norm, and a stable C. You can't just optimize one in a vacuum.
Okay, let's transition now to that third and final layer, federated learning. This handles the most restrictive cases, right? Where data simply cannot be moved.
Yeah, think about a massive multinational bank. Their data is probably regulated by a dozen different countries. Data from Germany can't leave German servers. Data from Singapore can't leave Singapore.
But the bank still needs one unified global model for things like fraud detection.
Exactly. Federated learning is the elegant solution that allows them to collaborate without centralizing the data.
So walk us through how that actually works.
It starts locally. Each client, a regional branch, a server, even a phone, trains a small local model on its own private data. And crucially, that raw data never, ever leaves its local environment.
So that knowledge gets to travel, but the person's records stay put.
That's the perfect way to put it. Second, only the model weights, the learned patterns, are shared with a central server. The server never sees a single transaction from a user in Mumbai or New York. It just gets these aggregated updates.
And the central server combines those updates using something like federated averaging to create a new, smarter global model.
And then that new global model's weights are sent back down to all the clients, updating their local models, and the cycle just repeats. And the global model gets stronger and stronger, informed by data it has legally never even seen.
So the main privacy guarantee here is structural. The server literally cannot reconstruct individual records just by looking at those aggregated weight updates.
Right. It allows collaboration at a huge scale while satisfying the most stringent data localization laws. And for the ultimate protection, you combine the layers.
How so?
You can use federated learning to keep the data local, and then you require each local model to add differential privacy noise, that's layer 2, to its weight updates before sharing them.
Which gives you the gold standard. Secure location, mathematical noise, and decentralized training.
That is the architecture of a trustworthy, production-ready AI system today.
Okay, let's quickly recap this full three-layer stack for you. We've really moved from just abstract ideas to the practical engineering that global companies need.
We detailed the 3 safety shields. Layer 1, operational privacy, keeping the data physically and structurally secure. Layer 2, differential privacy, which is all about applying that rigorous mathematical noise and managing the epsilon trade-off with things like date norm and C.
And layer 3, federated learning. The brilliant architectural fix that lets you build a global model without ever centralizing sensitive data.
If you understand those 3 layers, operational, differential, and federated, you really understand the entire pipeline that's required to earn the public's trust in this new age.
And that takes us right back to where we started. Trust is the true currency of AI. If a person can't trust you with their data, they're not going to trust your model. And it doesn't matter how fast or how accurate it looks on paper.
This whole transformation from theory to real-world architecture is what makes responsible AI development so challenging, but also so incredibly essential.
So we'll leave you with this final thought to consider in your own work. Anyone can train a model, but not everyone can build a model the world can trust.
It forces you to look beyond just accuracy metrics and ask a harder question. Have I actually engineered for trust? And what is the real quantified privacy cost of my model's utility?